Good afternoon. I almost said good morning, but that is no longer appropriate. Let's see. Today is Wednesday. Our second to last Wednesday of the summer session. Let's see. We are continuing on in chapter 10. Thanks to everybody, by the way, who came out to office hours tomorrow. Thank you in advance. Yesterday it was a really good time, really good conversation. It was jam-packed. I think there was like questions non-stop, and this was the first one where we actually didn't have a chance to finish them all. So anyways, tomorrow should be just full to the brim as well. I'll try to be as efficient as possible, and let's go ahead and dive into today's lecture material. So again, we are in chapter 10, and we left off talking about KAs and KBs, right? Just by way of recap, the Ka is the acid ionization constant. All right, and it tells us it's the simple equilibrium constant for the reaction of an acid with water to produce hydronium, which is aqueous, and the conjugate base, which I'm just going to write as A minus, right? So it's equal to products over reactants as always. So the molarity of hydronium times the molarity of the conjugate base divided by the molarity of the acid. And we said yesterday that because this is a ratio of products to reactants, the larger the Ka, the stronger the acid. The strongest acids near complete ionization, right? No HA left, all hydronium and conjugate base. Weaker acids, it tends to be more of a balance, but the larger our acid ionization constant is, the stronger the acid will be. Now, Ka isn't the only value used to rate acid strength. We can also use something called percent ionization. All right, so percent ionization is the percentage of the acid, which again we're abbreviating as HA, the percentage of the acid that has ionized into hydronium H3O plus and A minus. All right, so for example, if you had a 0.100 molar solution of HA, let's say this acid has a percent ionization that our percent ionization for this acid equals 25%. What that means in this reaction between the aqueous acid and water so it'll make, again, the products are hydronium and the conjugate base. If it has a 25%, if the percent ionization is 25%, what that means is 75. So we had an initial concentration of 0.1 molar HA. That means 75% of the acid is still associated, only 25% ionized. It also means, if you have this 25% ionization, that your concentration of hydronium and your concentration of the conjugate base will be 25% of that initial concentration. All right, so that percent ionization tells you that at equilibrium, we'll have a concentration of 0.75 molar for HA, and that the concentration of hydronium will be, oh, whoa, my eraser's crazy small. That our percent ionization is, that our concentration is 0.075 molar for HA, and that our concentration of the of hydronium is 0.025, and the concentration of A minus is also 0.025. All right. So the percent ionization tells you how much is splitting up, how much of that initial acid is splitting up, and it tells you what, or you can use it to determine your equilibrium concentrations. Of your acid, of hydronium, and your conjugate base. Again, we don't really pay attention to water because water is a pure liquid. It doesn't have a concentration per se. All right, now we can use this concept of percent ionization. It'll show up in a couple places, but for now we can use it to solve problems like this. So consider the following example. What is the equilibrium constant, the acid ionization constant, Ka, of a 1.00 molar solution of an acid, HA, whose percent ionization is 6.0%. All right. Now, this may seem like it's coming completely out of left field, right? Like, completely out of left field. But remember, we're dealing with an acid ionization. So we're dealing with the reaction of HA and H2O to make hydronium and the conjugate base. The equilibrium constant, Ka, Ka equals the concentration of hydronium times the concentration of A minus over the concentration of HA at equilibrium. So to calculate, and that's what we're trying to do here, right? We're asked, what is the Ka? To calculate Ka, we need three things: the concentration of hydronium, conjugate base, and acid in solution at equilibrium. To get there, we saw this just on the previous slide. You take the concentration to find the concentration at equilibrium for hydronium and conjugate base. You take the initial the initial concentration of acid, and you multiply it by the percentage you're given. In this case, I'm going to move this over here. .060, right? That's 6% as a decimal. To find the concentration of the acid, we have to multiply our initial concentration by 0.94, right? Because if 6% ionizes, that means 94% stays associated. So the concentration of our acid, HA, at equilibrium will be 0.940 molar, whereas the concentration of hydronium and conjugate base will both be 0.060 molar. And now that we know the two concentrations in our numerator and the concentration in our denominator, we can calculate a value for Ka by plugging these numbers in. So we have 0.060 for our hydronium, 0.060 for our conjugate base, and then we have 0.940 for our molarity of HA. You may be wondering why I'm not using units. It's because the equilibrium constant, I may have forgotten to mention this before, is a unitless quantity. So you never include units for it. All right, let's crunch our numbers. So we have 0.06 times 0.06 divided by 0.940. Our answer here is 0.0038298, but we can only keep 2 sig figs because of our numerator, and 2 is going to round down, so our final answer for our acid ionization constant is 0.0038. Let's see, Kate, why are there 3 sig figs for the acid? Okay, great question. So our molarity. So here's the reason why. So our we have 6.0% ionization, right? But our acid remains associated. So to find how much remains associated, we have to take 100%, subtract the percent that gets ionized, and that's where we get that 94%. 94%. This is associated. Which is what we use for HA. Now you'll notice that this is measured. Your percent ionization is measured. But when you're subtracting it from 100, this guy right here is exact. So your 100% won't limit your sig figs. Your measured quantity does, and it is precise to the first decimal place. So our answer has to be precise to the first decimal place. And when you write 94.0 as a decimal, it's 0.94, but then you have to have the same number of sig figs. So that's the reason why it's 0.940 has to do with this subtraction when you subtract 6.0% from 100. Hopefully that clears things up, Kate. That was an excellent question. In the final analysis, it doesn't affect our answer at all because we have 3 sig figs in our denominator here, but our numerator only has 2. So our answer still has to have 2. So it won't affect our answer in the end. But that's the reason why it's there, because it's procedurally correct. All right, we will see more of percent ionizations a little bit later today, or possibly at the beginning of lecture tomorrow. But for now, I want to move on to one of my favorite reaction classes that we talk about in this class, and that is the neutralization. The neutralization reaction. All right, now a neutralization reaction is a reaction between an acid and some sort of metal hydroxide base. So hydroxide with some cation. And these two react to produce two things every time. Every acid-base neutralization always reacts to produce water, liquid water, and some sort of ionic salt. All right, salt is just a term for some ionic compound, and this particular salt will have the cation that was involved with your metal hydroxide, and the anion will be the conjugate base of your acid that reacted here. Now, it'll always produce water and salt, and that salt will be determined by the specific acid and specific metal hydroxide used. All right. You may notice that I did not tell you the phase of your metal hydroxide or your salt. The reason why I didn't give the phase is because it'll be different each time, depending upon what metal is paired with the hydroxide and then what the cation and anion are for your salt. So you will have to figure out what phases go there using your solubility rules. All right, so you use the solubility rules to determine those two phases. The second thing that I want to point out here And this is the reason why professors love neutralization reactions, is that I do not have to tell you what the products are. When I ask you to balance this chemical equation. All right. I don't have to tell you what the reactants are, which is awesome. I can just tell you, sorry, I don't have to tell you what the products are. I can just tell you the reactants, and you get to go to town. All right. And if that sounds terrifying, then let's do an example. All right. So write a balanced chemical let's see, actually I'm gonna run out of space, just put it over here. A balanced chemical equation for the following neutralization. Let's sort of write that a little smaller. All right, and the following neutralization is aqueous hydrochlorous, not hydro, aqueous chlorous acid and sodium hydroxide. All right, now the thing to remember is this reaction is going to produce two things. One, it's going to produce water, so you can instantly write that in. All right, the second thing this reaction will produce is a salt. And the salt will be based on the cation from the base and the conjugate acid, right, A minus, from the acid we're given. Now, we can figure out what A minus is. We just have to look at what our acid will turn into once it donates a proton. Well, once it donates a proton, it'll have one less hydrogen, and after it loses that positive charge, it'll have a negative charge left behind it. So our salt will have a cation that is positive sodium, an anion that is ClO2 minus. So that means that salt, the identity of that salt, is NaClO2. All right. Now we've got to figure out what our phases are. And actually, I wrote the phase for sodium hydroxide, which I shouldn't have. I should have let you figure that out. But we know that any compound with a sodium cation will be soluble, according to the solubility rules, right? Anything containing sodium is always soluble. And since our product also contains sodium, NaClO2 has a sodium cation, it too will be soluble. So these are the products of this reaction. Now we need to balance it. All right, so in this reaction, we have hydrogen, chlorine, oxygen, and sodium. Ah, yes. Susan, great question. Sodium will always be the cation. That is one rule it will always assume. So we have hydrogen, chlorine, oxygen, and sodium. Hydrogen, we have 1 plus 1. Chlorine, we have 1. Oxygen, we have 2 from our acid, 1 from our base, and then we have our 1 sodium. On the product side, we have 2 hydrogen, 1 chlorine, 1 plus 2 oxygen, and 1 sodium. Turns out that we are already balanced, so this is our final answer. But I'm sure you can imagine, though I may sneak pre-balanced equations into the exam from time to time, not every example will roll that way. So let's take a look at another one where we might have to do a little more legwork. So let's write a balanced chemical equation for this neutralization reaction that takes place between hydrobromic acid, which is aqueous, and magnesium hydroxide. All right, now hydroxide is usually insoluble, right? Magnesium is not on the solubility list, so this will be a solid. All right, so we need to figure out what our products are. We know for starters Corinne's a good question. I believe it's in chapter 8. So our products here are going to be water and a salt. We need to figure out what that salt is. Right? And we know that our salt is going to be made up of our cation, which is Mg plus 2, and our anion, which is bromide, Br minus. So bromine has a charge of -1, magnesium has a charge of +2, so these come together in a 1-to-2 ratio. There's 2 bromides to 1 magnesium, and bromide is usually soluble according to the solubility rules, and it's insoluble with lead 2, mercury 1, and silver. Because magnesium's not on that list, we can write aqueous as the phase for magnesium bromide. All right, now that these are balanced, or sorry, they're not balanced yet. Now that we've written our reaction, let's balance this chemical equation. We have hydrogen, bromine, magnesium, and oxygen. These are the elements we need to balance. All right, we have 1 hydrogen from our acid plus 2 from magnesium hydroxide. We have 1 bromine, 1 magnesium, and then 2 oxygens on our reactant side. On our product side, we have 2 hydrogen, 2 bromine, 1 magnesium, 1 oxygen. All right, now I'm going to start with balancing my oxygen because it looks straightforward. I have 2 on my reactant side. I need 2 on my product side, so I'm going to multiply water by 2. This balances oxygen, changes hydrogen, but we're not concerned. We're going to just keep rolling. Now magnesium's balanced. Hydrogen doesn't look straightforward, right? 3 doesn't go into 4 evenly, but bromine looks pretty easy, right? 1 goes into 2 twice, so I'm going to multiply HBr by 2. This balances bromine, and you'll notice when we multiply that 1 hydrogen coming from HBr by 2, we get 2 plus 2 hydrogen, or 4 hydrogen, on our reactant side. So this balances our chemical equation in one foul swoop, or maybe a couple. All right, so it's not that much different than what we've been doing up to this point. It's still balancing chemical equations. I guess the only difference is now I'm not telling you what the products are. You have to determine that for neutralization reactions. All right, now neutralization reactions are also awesome because I can ask stoichiometry questions about them. So consider the following example. How many grams of water are produced when 25.0 milliliters of 0.100 molar sulfuric acid, which is H2SO4, are mixed with 35.0 milliliters of 0.100 molar barium hydroxide. All right. So stoichiometry, acid bases, solutions. It's combining so many concepts from different things we've looked at. It's just an excellent opportunity to test for multiple things all in one problem. It really is a beautiful thing. Step number 1 of this process, we need to write out our balanced chemical equation. We have sulfuric acid, H2SO4, reacting with barium hydroxide to produce water, all right, and our salt. Now our salt is going to be made up of barium, will be the cation, charged +2. The conjugate base here, what's left over after H2SO4 donates both of its H's, is a molecule of sulfate, right? SO4 with the -2 charge. This is one of our polyatomic ions. And so these will combine in a 1-to-1 ratio. All right. Whoops. So these are the reactants and the products of our chemical equation. Now we need to balance them. So we have hydrogen, sulfur, oxygen, and barium. So we have 2 plus 2 hydrogens, right? 2 from our acid, 2 from our base. We have 1 sulfur. We have 4 oxygens plus 2 more, 4 from our acid, 2 from our base, and then 1 barium. On the product side, we have 2 hydrogens, 1 sulfur, 1 plus 4 oxygen, and 1 barium. Sulfur and barium are both balanced, but water is not, right? Hydrogen and oxygen are not. I'm going to multiply water by 2 to balance my hydrogen and oxygen all in one fell swoop. All right, so this is our balanced chemical equation. And we'll use this to do our calculation. All right, now what we've been given here, we've been told that we're mixing right? We're mixing a 0.100 molar solution of sulfuric acid with a 0.100 molar solution of barium hydroxide, and that we have 25.0 mils of sodium hydroxide and 35.0 mils of barium hydroxide. All right, so what we have here is a limiting reactant problem. We need to find how many grams of water are produced, and we've got 2 initial starting quantities of 2 reactants. So we need to do the calculation with each initial quantity. Whichever one is lower will be our theoretical yield of water. All right, so I'm going to move my balanced chemical equation up just a little bit. All right, and now we can go to town. So if we start with sulfuric acid, we have 0.100. Now molar, that's moles of H2SO4 over liters. All right, and we want to get rid of our denominator, so we're going to multiply by our volume converted to liters. So that'll be 0.0250 liters. All right, next we need to convert from moles of sulfuric acid to moles of H2O. And the ratio here is 1 mole of sulfuric acid produces 2 moles of water. And then finally, we got to convert from moles of water to grams of water. And the molecular weight of water is 18.02 grams of water in 1 mole. All right, so now we got to crunch our numbers. We have 0.100 times 0.0250 times 2 times 18.02. So this comes out to be 0.0901 grams, 3 sig figs, are all we can keep. Now we have to repeat this process with barium hydroxide, 1.00. Now, molarity is moles over liters. And we need to multiply this by our volume, but converted to liters, so 0.0350 liters. Next, we convert from moles of barium hydroxide to moles of water. And this, just like the previous calculation, is a 1 to 2 mole ratio. Finally, we use the molecular weight of water to convert from moles to grams. All right, we can crunch our numbers here. 0.1 times 0.035 times 2 times 18.02 is 0.126 grams, and we got to roll with the lower one. So our theoretical yield of water is 0.091 grams. Okay, hang on. Hang on one sec. Okay, so sorry. Okay, Parthana, great catch. So the the solubilities here. Your acids are always aqueous. Hydroxides are usually insoluble, but hydroxides are soluble with barium. Water's a liquid, and then barium sulfates are usually soluble, but they're insoluble with barium, so that'll be a solid. So those are the solubilities. Awesome catch, by the way. Okay. So we've been, we're in the acid-base chapter. We've been talking about acid-base reactivity, right? Neutralization reactions being an example of that. We've been talking about not solubility. We've been talking about Bronsted-Lowry definition, how acid bases react, and we've talked about Ka, the acid ionization constant, which tells us how strong an acid is. All right, and now I have a question. A question for you. What is more dangerous? So here's my question. Which is more dangerous? A dilute solution of strong acid or a concentrated solution of weak acid. What would be more dangerous? All right, we've talked about concentrations of acid, we've talked about acid strength, and so the question is, what's more dangerous? Would you rather get splashed on your skin by a dilute solution of strong acid or a concentrated solution of weak acid? And the answer to this question, really, is it depends, right? It depends upon how dilute the dilute solution is. It depends upon how concentrated the concentrated solution is, right? There are solutions of hydrochloric acid, which is a very strong acid, but there are solutions that are so dilute that they'd be safe to drink. You'd never know the difference. They'd be fine. There are solutions of acetic acid, which is the thing that gives our balsamic vinaigrettes flavor. So we eat acetic acid on the regs if you're into that kind of thing. There are solutions of acetic acid that are so concentrated that they'll blister your skin if it comes into contact with it. So the answer to the question, what's more dangerous, a dilute strong acid or a concentrated weak acid, really depends upon how dilute or how concentrated. But the point of this question isn't so much to find an answer, but to get us thinking about the acidity level of a solution. We've been thinking about individual acids. How strong is this molecule? How strong of an acid is this molecule? How reactive is this molecule? But really, when you start talking about acidic solutions, you could have a very weak acid that has a very high concentration, and so the solution could be dangerous even though the acid is weak, right? Now, the point really of this question is to start to get us to think about solution acidity, not just the acidity of a molecule, but the acidity of a solution. And the acidity of a solution is determined by, whoa, Photoshop's flipping out. There we go. Is determined, the acidity of a solution is determined by its molarity, its concentration of hydronium. The more hydronium that's in solution, the more acidic the acid solution will be. All right. Now, discussion of solution acidity will inevitably lead to talking about pH, the pH of solution. That's where we're headed. Yeah, totally. But this conversation begins. So we're going to end up. It'll end talking about pH, but it has to start with a phenomenon known as the self-ionization of water. All right, the self-ionization of water. So, as we know, water is capable of being both an acid and a base, right? So what happens when one water molecule meets another in a dark alleyway where nothing else is around, right? What happens when one molecule... Whoa! All of a sudden my brush got super big. There we go. What happens when one water molecule bumps into another one? Well, this water molecule is going to be an acid, and this water molecule is going to be a base. So, Bronsted-Lowry definition of acids and bases: H2O, when it's a base, will accept a proton, so it will become H3O plus. And when water is an acid, it donates a proton, so it will become hydroxide, OH minus. All right. Now we can write the an equilibrium constant for this reaction. It's called Kw because this is the water ionization constant, and it is reactants. Sorry, not reactants. It is products over reactants. So the concentration of hydronium times the concentration of hydroxide over 1. You'll notice that both reactants here are in the liquid phase, so they are not included in the equilibrium constant. So Kw is just equal to H3O plus times OH minus, and the value for the water ionization constant is 1.00 times 10 to the negative 14. All right, that is the value for this equilibrium constant. It's very small, so you can tell that this equilibrium favors the reactants over products, right? Because it's very, very tiny. But there's a couple things that I want you to take away from. This happens, this self-ionization of water happens anytime, every time you have water that's in contact with water. So technically, there's no such thing as pure water, because if you have water by itself, it will react with itself in this equilibrium. So you'll have small amounts of hydronium and hydroxide present in every sample of water you touch. All right? Now, so that's one thing. The second thing, and this is a big deal, you'll notice that when you multiply the concentration of hydronium in a sample of water by the concentration of hydroxide in a sample of water, it equals a constant number. Right, that constant number is 1.00 times 10 to the negative 14, but you multiply them together, they will always equal the same thing. That means that if your concentration of hydronium increases, your concentration of hydroxide has to drop. It also means that if your concentration of hydroxide increases, that your concentration of hydronium has to drop, because when you multiply them together, no matter what those values are, they will always multiply to be equal to 1.00 times 10 to the negative 14. All right? So this fact that the water ionization constant is hydronium times hydroxide equals this constant number allows us to solve all sorts of problems. It also means that you cannot increase the amount of acid in solution without decreasing the amount of base. These two are inversely proportional. You will never have a solution that has a large amount of acid and a large amount of base together. It's not physically possible. All right. Now this reality, though, does allow us to solve problems like the following. So Just bear with me real quick. I'm going to rewrite the water ionization constant. All right, and this is 1.00 times 10 to the negative 14. Okay, we can solve now examples like the following. What is the concentration of hydronium in a solution with where the concentration of hydroxide is equal to 0.100 molar? All right. Well, to solve a problem like this, we need this equation. So I would keep it at the ready. Again, this won't be on exam 2. Sorry. This won't be on exam 3. This will be on the final. But I would keep this equation at hand because you'll notice you always know Kw, right? It's constant. We've been given hydroxide, so we can solve for the concentration of hydronium if we divide both sides by the concentration of hydroxide. So they cancel there, and our concentration of hydronium is equal to, Kw is 1.00 times 10 to the negative 14, and the concentration of hydroxide is 0.100. So when you divide one by the other, we get that the concentration of hydronium is 0.100 times 10 to the negative 13 molar. Right, we've got to have units of molarity as part of our answer because that's what those brackets are mean. That's what those brackets mean. All right, so there's one example of one example where we can use the water ionization constant to solve a problem. But that one was fairly straightforward. Let's do one that's a little on the harder side. All right. What is the molarity of hydroxide in a solution of 3.00 molar hydrofluoric acid? We need one more piece of information. Hydrofluoric acid has a 2.6% ionization. All right, so here's the deal. We're being asked about the concentration of hydroxide. So we know on some level that we're going to need the acid ionization constant. Right, we're being asked to find the concentration of hydroxide. We know Kw, but to find hydroxide, we are going to need to figure out what the concentration of hydronium is. All right, what is the concentration of hydronium? And that is where our percent ionization and our molarity of HF come into play. We've done percent ionizations before, right? We have hydrofluoric acid reacting with water to produce hydronium plus our conjugate base, which is fluoride for HF. All right, now we know that the concentration of hydrofluoric acid is going to be 3.0 molar times, well, actually, hang on. Actually, before we even talk about that, the concentration of our products, both fluoride and hydronium, are going to be equal to that initial molarity of HF times the percent ionization. Right, the concentration of HF is going to be equal to that initial molarity times the difference in the percent ionization at 100%. So this would be times 97.4%. All right. Now, we don't have to crunch all these numbers because really the only one that we're interested in is the percentage or the molarity of HF. Sorry, not HF. The molarity of hydronium. So at equilibrium, this will have a concentration of 0.078 molar. And now we can use the equation for the ionization of water to solve for the molarity of hydroxide. So we get hydroxide is equal to, the molarity of hydroxide is equal to 1.00 times 10 to the negative 14 over 0.078. Crunch our numbers, and they come out to, let's say we can keep two sig figs, 1.3 times 10 to the negative 13 molar OH. That is our answer. All right, so that is the molarity of hydroxide in a solution of 3 molar hydrofluoric acid, which has a percent ionization of 2.6%. So you use the concentration of your acid and the percent ionization to find your molarity of hydronium in solution. Then you use the ionization of water to find your molarity of hydroxide. All right. I'm looking at the time. I have one more example with this equation, and I'm going to write it on the board, and we're going to start with this tomorrow. Kate, great question. So, and this is good whenever you're given the percent ionization. Whenever you're given, aliens are writing to us. That is a secret alien communication, but I've got to scrub it out of the video before the government hacks my YouTube channel. So there's the percent ionization. Whenever you're given the percent ionization for an acid, you always write the equation for the ionization of that acid with water. So the reaction of whatever your acid is, HA, plus water, producing hydronium, hydronium and your conjugate base. All right, in this case, the acid we were given, that sounds, don't ever just take the acid that you're given. The acid we were given was hydrofluoric, especially if it's hydrofluoric acid. So you do hydrofluoric acid reacting with water to produce hydronium plus, now our conjugate base is what's left over after HF drops off its proton, donates its proton, so it'll just be F minus. So that's where the chemical equation comes in. Or the chemical equation comes in because we're given percent ionization for an acid, so we need to write out the equation for that acid ionization. All right, so this is the acid ionization of hydrofluoric acid. We then use the percent ionization to figure out how much hydronium is in this solution, and once we know how much hydronium, we use the ionization of water to solve for the amount of hydroxide present. Susan, that is correct. I wanted to show it for completeness. Whoops. It is tricky. Totally tricky. Okay, so let me write up this example. This is what we'll start lecture with tomorrow, and then we'll call it a day. So let's see. Oh, right. Our last example. Here's a question. What is the concentration of hydroxide and the concentration of hydronium in a solution where there are equal amounts of both equal amounts of both? You heard me. Tune in tomorrow to see if your answer to this thrilling question matches the answer to this thrilling question. I'll catch you guys all in about 24 hours. Have an awesome Wednesday. I had to think about what day it was. Later.